Hello there and welcome back to the Science Sleepy Minds. Outside your window, the night presses in like velvet, soft and unknowable. Stars flicker against the dark canvas, pinpricks of ancient light that seem still and distant. But they're lying to you. Everything is moving. Your planet, your body, even time itself. And as you listen, comfortably tucked in, your atoms buzz quietly while the universe hums a tempo you can't quite hear. You're not just drifting off to sleep tonight, you're sliding through time and not at the same speed as the rest of existence. You're already a time traveller, you just don't feel it. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and your local time in the comments. I love seeing where and when you're tuning in from. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're lying still, but the world spins beneath you. The Earth rotates at about 1,000 miles per hour, or 1,600 kilometers per hour if you prefer. It's also orbiting the Sun at around 67,000 miles per hour. And the entire solar system? It's zipping through the Milky Way at a breakneck speed of 514,000 miles per hour. And yet, your blanket feels still. Your breath rises slow. Your room doesn't tilt. You're in motion at cosmic scale, and you're entirely unaware. But time knows. Time feels every tick of those motions. Here's where it starts to get delightfully weird. All that movement means you're experiencing time differently than, say, a satellite, or someone lounging on the International Space Station. You aren't aging at quite the same rate as someone else zooming through a different gravitational or velocity field. It's not sci-fi, it's just physics. According to Einstein's theory of relativity, one of those big brain-melting ideas that turns reality into a funhouse mirror, time is not absolute. There's no master clock ticking uniformly across the universe. Instead, how fast time passes depends on how fast you're moving and how much gravity you're feeling. This isn't just theory, it's measurable, it's repeatable, it's happening to you right now. Picture two atomic clocks, one sits on the floor, the other gets lifted just 1 meter higher. After a little while, the clock that's higher off the ground runs faster. We're talking nanoseconds, but they're real, traceable, and yes, permanent. You've just created a tiny time machine by changing elevation. It's cute until you realise this means your feet and your head are aging at slightly different rates. Time ticks slower the closer you are to a massive object, like Earth. So, if you've spent a lot of time lying down, congratulations. You've been aging ever so slightly slower than your co-workers at standing desks. The difference is laughably small, but still, science is on your side. You might be wondering, if I can't feel it, does it matter? Oh, it matters. Because it scales. Go from lying in bed to flying in a jet and time slows down more. Go from a jet to a spacecraft orbiting Earth, and the shift becomes large enough to calculate with terrifying precision. Go faster, like approaching the speed of light, and time doesn't just slow, it collapses. A trip that lasts minutes for you could span decades for someone watching from Earth. Congratulations. You've skipped entire generations while sipping freeze-dried astronaut coffee. There's an old thought experiment, and we'll get into it more later, but it's irresistible now. Imagine you have a twin. You both grow up together, then one of you hops into a near-light speed spaceship, zips off into space, and returns. The one who stayed on Earth has aged 20 years. The one who travelled, maybe only aged 2. Same DNA, different timelines. No paradox, just physics laughing in your face. Historians still argue whether Einstein realised the full personal horror of this when he was doing the math. Probably not. He was too busy revolutionising science while forgetting to comb his hair. But let's stay in your room a little longer, just for tonight. Imagine you're completely still, not moving, not floating, just being. The funny thing is, even doing nothing, you're still travelling through time. In fact, you're moving through time at the maximum speed possible, because you're not moving through space at all. That's a twist of relativity. The more you move through space, the less you move through time, and vice versa. Think of space-time as a budget. You only get 100% to spend. If you use a lot of it for space, going fast, you have less left for time. That's why fast-moving objects experience time more slowly. That's why astronauts come back just a tiny bit younger. You can't feel it, but your whole existence is a balancing act between space and time. Your heartbeat, your dreams, even that embarrassing memory from middle school you randomly remembered today, it all unfolds in your personal stream of time. Meanwhile, galaxies spin and warp and collide, aging on their own schedules. Here's a strange one. There are places in the universe where time is essentially stopped. We'll fall into one of those soon enough. Black holes, I'm looking at you. But for now, just hold on to this idea. Time doesn't pass the same way for everything. Everywhere. Even clocks, our sacred, smug little machines, aren't exempt. The best clocks we have, atomic clocks, have confirmed over and over that time is local, subjective, personal even, which makes your bedtime routine less mundane and more like a ritual of temporal awareness. And as you sink deeper into your mattress, let me drop a delicious little fact. Astronauts aboard the International Space Station age about 0.007 seconds less every 6 months than those on Earth. It's nothing you'd notice, but they are very literally younger. Somewhere out there, science fiction high-fived reality. And it's not just humans. Some particles, like muons, live just millionths of a second before decaying, but when they're shot through particle accelerators at near-light speeds, they live longer. They outrun time's decay schedule. Not bad for a speck of matter. Time, it turns out, isn't a river. It's a flexible, fickle, high-maintenance diva that bends itself to motion and gravity. The stars overhead? They're not just distant, they're old in a way that's deceptive. Some of them might already be gone, and you're only just seeing the light that began its journey before humans had written language. So if you've ever had one of those nights where you stare at the ceiling and wonder, where did the time go? The answer is simple. It didn't go anywhere. It went somewhere else, at a different speed, on a different trajectory, laughing gently as you counted sheep. And you? You're not running out of time. You're just riding a very complicated, very personal wave through it. And you feel heavier here on Earth than you would floating in orbit. And that weight, your weight, is the invisible hand of gravity pressing down on you. It's not just holding you to the ground, it's also dragging your seconds just a little slower. Time, under the influence of gravity, doesn't pass evenly. And your comfy position, deep in the planet's gravitational well, means your clock is ever so slightly behind someone perched higher up, even if they're just chilling in an airplane seat. Gravity doesn't just pull, it slows. That's the unsettling part. You think of time as a straight arrow, ticking away second by second, evenly and endlessly. But the moment gravity enters the equation, it's more like syrup sliding down an uneven slope. This isn't metaphor, it's how the universe works. More mass means stronger gravity. Stronger gravity means slower time. It's a feature of space-time, one of the wild insights gifted to us by general relativity. When Einstein worked this out in the early 20th century, the scientific world pretty much went, wait, what? The idea that gravity isn't just a force but a curvature of space and time itself, that was revolutionary, and the consequences, utterly strange. A stronger gravitational field actually bends space-time more steeply, which means that in the deep valley of Earth's gravity, time runs just a little slower than it does up on a mountain. In 1976, the Gravity Probe A experiment proved this. Scientists launched a hydrogen maser clock aboard a rocket to an altitude of about 10,000 kilometers. It ticked faster than its twin left behind on Earth. Not just by theory, by measurable, countable amounts. We're talking nanoseconds again, but let's face it, time dilation isn't here to be dramatic. It's here to mess with precision. If you've ever wanted to feel like a science wizard, consider this. Every time you go to the beach from a mountaintop, you're entering a slightly slower stream of time. Congratulations, You're aging at sea level just a fraction slower than you did 3,000 feet up. Not enough to skip a birthday, but enough to make atomic clocks raise their eyebrows in surprise. The effect becomes more pronounced the stronger the gravitational field. So, let's head to Jupiter. Not literally, don't pack your bags just yet. Jupiter's gravity is much stronger than Earth's. If you could stand on its surface, you can't, it's gas, but go with it. Time would crawl compared to your cozy bedroom. The more gravity pulls, the more time drags. And if you edge towards something like a neutron star, where a teaspoon of matter weighs more than a skyscraper, your seconds stretch even further. Now imagine standing near a black hole, not inside, don't worry, that's later, but hovering near the event horizon, the point of no return. From your perspective, your watch ticks normally, but from someone far away, maybe orbiting in a spaceship, your seconds look like they're stretching out. Your hand moves in slow motion. Your blink takes minutes. Your wave goodbye seems eternal. To the outside observer, you're frozen, suspended just above the black hole's surface forever. But from your point of view, everything's perfectly fine until, well, it's not. But again, that's for another section. Historians still argue whether the ancient astronomers, those Babylonian stargazers or Greek philosophers, had any inkling that the heavens might distort time itself. Probably not. They were busy measuring angles and predicting eclipses, but gravity, that was just a force to them, a pulling down, not a bending of reality. It took a shaggy-haired patent clerk in 1905 to flip the narrative, and then 10 years later, rewrite the book entirely. Today this idea isn't fringe, it's baked into your life. Your GPS wouldn't work without it. Wait, we'll get to that next time. Let's just savour this for now. Every mass you encounter in your life, your phone, your bed, your cat, has a gravitational field. Yes, even your cat is technically bending space-time around herself, which explains both her disdain and her ability to control time at 3 AM. But Earth, being significantly larger than your cat, has a more noticeable pull, and its gravity doesn't just hold the oceans in place or make apples fall, it subtly rewrites how fast everything unfolds. That's why astronauts age differently up there. Away from this pull, it's why satellites need time corrections, and it's why, if you ever want to live a slightly longer life, the top of a skyscraper isn't a bad place to start. But there's something else hiding in all this. Because gravity isn't just pulling and stretching time, it's also hiding information. When you look up at the night sky, those twinkling stars are already time-shifted. If one suddenly vanished in a puff of cosmic drama, you wouldn't know it for years. In some cases, thousands or even millions of years. Gravity and distance conspire to delay everything. The sky is lying to you, beautifully. This is why cosmologists, those folks who sit in dark rooms and ask questions like what is now, really, have trouble pinning down a universal present. What's happening now on a planet orbiting Alpha Centauri? We don't know, can't know, because by the time their now reaches us, it's already past. So next time someone tells you time is relative, don't just nod and smile. Realize it's not just philosophy, it's baked into the way you live. You're soaking in gravity, you're aging differently than someone orbiting above, and that hot tea you're sipping, it's aging faster than the teaspoon you dropped in it. Sort of. In a very, very nerdy way. And if that doesn't keep you up at night, maybe this will. All of these time differences, all this distortion isn't a glitch. It's not a trick of perception. It's reality. You and the universe are not ticking in sync. You never were. But don't worry, you've still got enough time to fall asleep to the sound of a fan and this gentle rambling, even if time is already doing its own thing. So you're still lying there, perfectly still. And yet your seconds are slipping past differently than someone racing 30,000 feet above your head. Not because your clock is broken, but because of something Einstein whispered to the universe over a century ago. The faster you move, the slower you age. That's time dilation through velocity, and it's about to get uncomfortably real. Let's say you're lounging on Earth with a friend, and your friend decides to hop aboard a hypersonic jet just to make the day interesting. They fly around the planet a few times at ludicrous speed and come back for dinner. You both look the same. You both feel the same. But they're just a little bit younger than you now, by milliseconds, sure, but younger nonetheless. They've squeezed time like an accordion and come out the other side. Speed limits don't just apply to cars and kids on scooters, they apply to time itself. As you approach the cosmic speed limit, aka the speed of light, time slows dramatically for you relative to everything else. It's not optional, it's how space-time behaves. You could be sipping tomato soup in a spaceship going 99.99% the speed of light, and your soup would be warm for 5 minutes by your watch. But back on Earth, decades could pass. Wars could start and end. Celebrities could rise and fall. Entire governments could flip. Meanwhile, you've barely finished your croutons. This isn't just theoretical babble. The math checks out. We've confirmed it in particle accelerators. Take muons, tiny unstable particles. Normally they decay in microseconds. But when we accelerate them close to light speed, they stick around longer. Like a lot longer. Time literally stretches for them while they're moving fast. That's time dilation in action, on a quantum scale. It's kind of beautiful if you ignore the existential dread. One of the earliest experimental proofs of this came in the 1970s, when scientists flew atomic clocks on commercial airliners around the world. Clocks that flew eastward lost a few extra nanoseconds compared to those that stayed home, and clocks flown westward gained a few. Not massive shifts, but enough to prove relativity wasn't just for lab coats and blackboards. It was happening on aisle 12 between a crying baby and an overpriced sandwich. Here's where things really twist. This isn't an illusion. It just looks like time is slower. For the person moving at high velocity, time actually is slower. Their heart beats slower. Their neurons fire slower. Their wrinkles show up later. They are living a shorter time relative to everyone else, not just observing it, experiencing it. Historians still argue whether Galileo or Newton could have ever seen this coming. Speed affecting time? That would have sounded like heresy in the age of powdered wigs and cannonballs, but Einstein built on centuries of motion and gravity study and tossed a hand grenade into the whole idea of universal time. He showed that time and space are part of the same fabric, and that when you move through one, you bend the other. So why haven't we built a time machine yet? Because there's a catch. There's always a catch. You can't go faster than light. It's not just hard, it's impossible. The faster you go, the more energy you need to keep accelerating. Get close to light speed, and the energy needed approaches infinity. At exactly light speed, you'd need infinite energy, which is a little over budget. But you don't need to reach light speed to time travel, just approach it, and time starts behaving weirdly. This is where that famous twin paradox comes in, one of physics' most misunderstood tales. Let's say you and your identical twin are born at the same time. You stay home mowing the lawn and watching TV. Your twin. They hop on a spaceship and zoom away at near light speed. When they finally return, you've aged 50 years. They've only aged 5. You're old and grey. They're still young enough to get carded buying wine. But here's the catch. It's not a paradox. The confusion comes from thinking the situation is symmetrical. If I'm moving away from them, then they're also moving away from me. True, but only one of you turned around. Only one experienced acceleration. That breaks the symmetry. Your twin felt the jolt of reversing direction in space. You did not. Therefore, they experienced less time. And yes, this is real. We haven't done it with humans, yet, but we've seen it in particles. We've even planned future missions that could push this effect further. Imagine astronauts returning to Earth biologically younger than their grandchildren. Time dilation isn't just about how fast you go either. It's how you get there. Acceleration plays a role. You can't just zip through time without feeling the forces involved. And once you're going fast, it's not just your clock that ticks differently. Your whole sense of now warps. The universe tilts around your motion. This leads to the really weird stuff. Simultaneity goes out the window. Two events that happen at the same time for you might not be simultaneous for someone else moving quickly past. Light flashes, explosions, alarms. None of it is anchored in universal time. There is no absolute now. The faster you move, the more your now becomes your own private version of reality. So that moment you're having right now, lying there, listening, breathing slowly, somewhere else, it hasn't happened yet. Somewhere else it already has, and in a fast-moving spaceship, it might never line up with another moment again. Let that sink in with your pillow. So yes, speed messes with time, and you don't even need a warp drive to feel it. Just flying on a plane, or standing at a different latitude, or orbiting in a satellite, your seconds slip, not by much, but enough for us to track, and once you know this, you can't unknow it. You start looking at every train, every rocket launch, every satellite overhead, and thinking they're living in slightly different time zones, not by hours, but by physics. It's not jet lag, it's space-time lag. So if your alarm ever feels off by just a hair, maybe it is. Maybe your corner of the universe is ticking a little differently today. Maybe your day really did slip a second shorter while someone else is stretched. Or maybe time, like always, is just reminding you who's really in charge. Let's say you have a twin, a real one. Same birthday, same awkward haircut in 6th grade, same inherited tendency to sneeze when walking into sunlight. Now imagine this twin of yours is a bit more adventurous. They've just volunteered to be the first human to ride a spacecraft capable of approaching the speed of light. You, meanwhile, have decided that Earth's gravity, breathable atmosphere, and access to pizza are too good to pass up. So, you stay. Your twin rockets away into the cosmos at 99.999% the speed of light, zipping around a nearby star and coming home a few years later by their clock. You greet them at the landing pad expecting a reunion of equals, but they don't look like you anymore. They look younger, not in a new moisturizer kind of way, in a they somehow skipped 20 years of aging kind of way. While you lived 2 decades of work, sleep, streaming shows and birthday candles, they only experience maybe 2. That's the twin paradox, and it's not science fiction. It's a real-world consequence of time dilation through velocity. The faster your twin travelled, the more time stretched for them, and the less they aged. While you were busy getting annoyed by commercials on streaming services, they were skipping forward in time like it was a cosmic fast-forward button. And this isn't a quirk of the math, it's been experimentally verified. Muons, those unstable little particles we met earlier, they decay quickly when at rest, but zoom them through a particle accelerator near light speed, and they live much longer. It's like someone pressed pause on their biological clock. The twin paradox isn't a paradox at all, really. It only seems like one until you remember that the travelling twin experiences acceleration. First as they leave Earth, then again when they turn around, and once more as they decelerate to land. Those bursts of acceleration break the symmetry. You, this stay-at-home twin, are in an inertial frame. No major acceleration. Your sibling, meanwhile, gets the cosmic whiplash. Their time path through space-time is different. Shorter, even. In terms of aging, they've taken the shortcut. Historians still argue whether Einstein truly grasped how deeply unsettling this would be for regular people. Not just that clocks tick at different rates, but that 2 people who start in the same place, with the same DNA and the same birthday, can end up with different amounts of lived time. It's not just physics, it's philosophical dynamite. What even is age, if it's no longer a constant? But don't worry. The story of your long-lost twin doesn't end with you resentfully baking them a belated birthday cake. It ends with awe. Because what they've experienced, what you both have experienced, is a reminder that time is not fixed. It bends, it flexes, and it plays favourites. Now imagine scaling that up. Picture interstellar explorers hurtling across the galaxy at incredible speeds. They leave Earth in the 23rd century. For them, a trip takes 5 years. But back home, a century passes. They return to a world transformed. New languages, new borders, new snacks. Their original mission debrief is now a historical artifact. And while they've only added a few years to their own lives, they've outlived everyone they knew. It sounds like a plot from a movie because it is, many times. But it's also the real math of relativity. The faster you go, the more your timeline diverges. You don't just travel through space, you travel into the future. You skip ahead, not by cheating time, but by leaning into its rules. There's a beautiful, eerie symmetry to it. You want to age less, just move faster, but that motion requires energy, acceleration, risk. And at the human scale, right now it's not very practical. Unless your twin is willing to spend a few $1 trillion on a custom light-speed rocket, you'll likely age together at a comfy earthbound pace. But here's the twist. It's already happening. Every astronaut aboard the International Space Station comes back fractionally younger than they would have if they'd stayed on Earth. Just a few milliseconds, but real, measurable, non-negotiable milliseconds. The faster they orbit, the slower they age. In fact, astronaut Scott Kelly, who spent 340 days aboard the ISS, came back measurably younger than his twin brother, Mark Kelly, who stayed on Earth. It wasn't enough to start growing backwards, Benjamin Button style, but it happened. It's real. And if that makes your bedtime feel like a time machine, well, that's because it kind of is. You're not aging in lockstep with the universe. You're surfing a local version of time that's being shaped by your motion, your location, and your gravitational environment. But wait. Here's a fringe nugget to roll around in your half-dreaming brain. Some scientists and philosophers argue that time itself might not be fundamental at all, that it's an emergent property, something that arises from deeper quantum structures we haven't fully uncovered yet. If that's true, your twin didn't just skip ahead. They danced across something that might not even exist the way we think it does. Yeah, sleep on that one. Let's zoom in again. Back to you and your twin. Imagine the reunion. Two siblings, both technically the same age, but with different counts of memories, wrinkles, stories. One of you has lived more than the other. One of you has seen more sunsets, breathed more breaths, blinked more blinks, and all because one of you moved faster. The universe doesn't care about fairness, it doesn't offer refunds or apologies. It simply shrugs and says, well, that's how space-time works. And while the twin paradox is a favourite among physics undergrads and sci-fi fans, it serves a deeper purpose. It reminds us that time isn't a fixed ruler stretching out evenly for everyone. It's a shifting, flexible thing that depends on how and where you move through it. So tonight, as you lie there under the gentle gravity of your mattress, know this. You're participating in a one-way journey through time. But if you wanted to, if you really wanted to, you could change your pace. Not backward, but forward. And faster than most people will ever experience. You wouldn't even need a DeLorean, just a ridiculously fast spaceship, or for now, a really well-funded science program. Until then, sleep tight. Your seconds are already slipping differently from someone else's. So, you're back on Earth. No relativistic spaceship this time. Just you, your phone, and a mild existential crisis about what time even is. You check your location, open Google Maps, maybe search for the nearest taco place that's still open at 2 a.m. Your GPS pings a few satellites and tells you where you are, down to a couple of feet. Here's the wild part. If those satellites didn't account for time dilation, your midnight snack craving would send you walking into someone's hedge. Seriously, without relativity, your GPS would be wrong by about 10 kilometers per day. That's nearly 6 miles of error, compounded daily. Every morning your commute would begin with, wait, why does Google think I'm inside the ocean? Let's unravel this. Global Positioning System satellites orbit Earth at around 20,200 kilometers above the surface, moving at about 14,000 kilometers per hour. That's fast enough for time dilation to kick in. And unlike your sleepy self, the atomic clocks aboard those satellites are outrageously precise, accurate to a few billionths of a second. At that level, even the tiniest discrepancy turns into a geographical mess. Here's where the double whammy of time dilation hits. First, there's velocity-based time dilation. Because the satellites are moving quickly relative to you, their onboard clocks tick slower than yours. This effect comes straight from Einstein's special relativity and causes their time to lag behind Earth-based clocks by about 7 microseconds per day. But second, those satellites are also way up in a weaker gravitational field compared to your couch potato position on Earth. And remember what we learned earlier, less gravity equals faster time. So thanks to general relativity, their clocks actually tick faster by about 45 microseconds per day. Combine those, and GPS satellite time runs about 38 microseconds faster than ground-based time every single day. Doesn't sound like much, right? But when light travels about 300 meters in a single microsecond, 38 microseconds means you're off by over 10 kilometers. That's enough to lose your car in a parking lot, or walk into the wrong restaurant, or if you're a missile system relying on GPS, miss your target by a town and a half. Thankfully, engineers bake relativity into every single calculation. GPS satellites are pre-programmed to slow down their clocks to counteract these effects. That's right, your phone knows about Einstein. It's applying corrections for the very same time-warping forces you're falling asleep to. Historians still argue whether Einstein himself imagined that his equations would one day power turn-by-turn directions and food delivery apps. Probably not. He was more into pipe smoking and train metaphors, but relativity isn't some abstract thing reserved for textbooks and labs. It's embedded in everyday technology, quietly keeping your digital life from unraveling. And GPS isn't the only place where time dilation plays a role. High-frequency trading on Wall Street? Those folks have to account for timing differences down to nanoseconds. Scientific instruments aboard orbiting telescopes? Also corrected. Even astronauts communicating with Earth have to adjust for the fact that time is ticking differently, depending on where they are. It's like every modern system is whispering, yes, yes, time is relative, please don't ruin the algorithm. There's a fringe but fun theory that as we build more precise clocks, ones accurate down to the zeptosecond level, we'll start noticing even more subtle time dilation effects, maybe even from earthquakes shifting mass or tides pulling on crustal plates. Imagine a future where your smartwatch doesn't just count your steps. It knows your elevation, your speed, and how time is bending just for you. Which of course makes you wonder, is everyone's phone aging at the same rate? Not quite. A phone left on the top floor of a high-rise technically experiences time slightly faster than one in a basement. Not enough to care about yet. But as our technology becomes more precise, and as we start building networks of ultra-accurate atomic clocks, these differences could start mattering in navigation, science, maybe even communications. It's a little unnerving, right? That your reality, your position, your speed, your altitude, is bending your experience of time, and your devices are constantly compensating for it. You're already living in a relativistic world. Your apps just don't rub it in. Still, if you ever want to feel like a low-budget time traveler, just remember, every text you send from an airplane, every time you rely on GPS to find an ice cream shop, you're depending on calculations that span Einstein's two greatest theories. And those theories are quietly, invisibly correcting your place in the universe. Here's another fun twist. The GPS network doesn't just help us find directions, it also lets us measure time globally. Since all GPS satellites are synced and constantly adjusting for relativistic drift, they create an incredibly accurate time standard. In fact, one of the most precise timekeeping systems in human history. Imagine that. You thought GPS was just to help you avoid traffic, but it's actually a massive orbiting time machine grid. And if you're ever at a party and someone mentions Einstein, and someone else says, "Oh yeah, didn't he do something with time?" You can lean in and say yes. And I use it every time I look for the nearest sushi place. Not every day that theoretical physics saves your dinner plans. So next time you check your ETA, remember, space, speed, and gravity have all been mathematically tamed just to tell you that you'll be late by 8 minutes due to traffic on Main Street. And if you really want to mess with your own head, look up at the sky and think about this. Each GPS satellite is ticking just a little differently than the others. Their time bent by tiny orbital variations, their speed and altitude unique, their clocks subtly out of sync. but harmonise by equations so elegant they feel like wizardry. And all of that, just so you can find your way home. You wake up in your own bed, or maybe you're still lying there, floating in that halfway space between sleep and thought. Either way, you have this strange feeling, like you're wrapped in your own little bubble. Because in a way you are. Your body is moving through your personal stream of time. It's not the universe's time, not your neighbours, not your dog's. It's yours, tied to where you are, how fast you're going, how close you are to mass. This stream flows uniquely for you, a private tempo in a universe that refuses to sink. Welcome to the idea of your time bubble, and it's not just a poetic metaphor. You're genuinely aging at a pace that's different from most other things in the universe. If that sounds dramatic, it's because it is. You and a galaxy on the far side of the observable cosmos are not experiencing time in the same way. Never have, never will. That's because of a hidden force most of us never think about: cosmic expansion. The universe isn't just big, it's growing, expanding, stretching like a vast invisible balloon. And this expansion has consequences not just for space but for time itself. Here's the unsettling truth. The farther away something is, the slower it seems to age from your perspective. Now hold on. This isn't about motion this time. It's not about how fast things are moving or how deep they are in a gravity well. This is something else. Something that arises from the fact that space itself is getting bigger. Between every pair of galaxies, new space is constantly unfolding. That means light, those messengers from the distant past, is taking longer and longer to reach us. Not just because it has far to go, but because the finish line is moving away as it runs. Imagine trying to walk across an airport walkway that's moving backwards under your feet. You make progress, but slowly. Light faces the same problem. It's travelling at its own max speed, but the space it moves through is stretching out underneath it. And because of that, the cosmic clock appears to tick slower the farther out you look. You might be lying comfortably in 2025, but the light from a galaxy 10 billion light years away is showing you what it was doing 10 billion years ago. No biggie, you already knew that. But it's not just distant in space, it's distant in time, and experiencing time more slowly in your reference frame. This isn't an illusion, it's built into the math of the universe. When we observe Type Ia supernovae, those bright standardizable explosions we use to measure cosmic distances, we notice something odd. They're like curves. The way their brightness rises and falls are stretched. It's not because the explosion itself is slower, it's because, in our frame of reference, their time has been slowed down by the expanding fabric of space. Astronomers account for this all the time. They call it cosmic time dilation. A supernova that takes 20 days to brighten and fade in its own galaxy might appear to us to take 40 days. The farther back we look, the more extreme the effect. You see a slowed down universe because you're here, on Earth, moving through your local time. But the distant universe is running on cosmic time, a framework that includes the whole expansion history of space-time. Historians still argue whether early astronomers had any inkling of this scale. Probably not. Ancient sky watchers charted the stars and planets as if they moved on a static dome. Even Copernicus, with his heliocentric revolution, had no idea the dome itself was stretching. It wasn't until the 20th century, thanks to Edwin Hubble and some very confused redshifts, that we realised the universe was expanding. And with that realisation came an uncomfortable thought. There's no universal now. There is no cosmic moment where everything in the universe is experiencing the same second. Because space is expanding, time gets smeared out. There is only your now, relative to your motion and your place in the gravitational web. Even weirder, the universe has its own clock. Cosmologists define a cosmic time that ticks from the Big Bang forward. But it's not the same as your wristwatch time. It's more of a universal average, an agreed-upon timeline based on an observer who's at rest relative to the cosmic background radiation. That observer, isn't you. Probably not even close. You're inside your own time bubble while the universe keeps ticking on a different scale. Light from the earliest galaxies reaches you time-stretched, slowed down, exhausted by the journey. And you, a barely conscious mammal wrapped in blankets, are living on a timeline that those galaxies may never truly understand or share. Here's a strange fringe thought. If someone lived billions of light years away, moving at a different speed, under a different gravitational environment, their concept of now might not overlap with yours at all. Not just by light years, but by eras. For all we know, their version of current reality might be our ancient past, or our future. It's all relative. Painfully, precisely, beautifully relative. And yet, your time bubble protects you, keeps your world cohesive. Your cereal doesn't age faster than your spoon. Your cat doesn't time warp while you're at work. Locally, within your gravity and your speed, time behaves predictably. It's only when you zoom out, really, really far out, that the illusion of synchronization collapses. Which, let's be honest, makes you kind of a time narcissist. You live in your own flow of seconds and assume that everything else shares it. But the stars, the galaxies, the microwave background echoing from the Big Bang, they don't care about your seconds. They have their own clocks, and they're ticking slower, faster, or sideways depending on where and when you look. You probably don't notice, not while brushing your teeth, not while doom scrolling in bed. But every bit of light that enters your eyes from the universe is subtly distorted by time, not just distance, dilation. So, as you drift off, remember, you're not aligned with the universe. Not really. You're floating inside your own pocket of space-time, watching distant events play out on delay. You're the star of a personal documentary where the rest of the cosmos appears in reruns, warped and slowed by cosmic context. And that's okay. You don't have to sync with the universe, you just have to enjoy the strange, slow show it's putting on for you. You've probably never had to think about which clock in your house is the most accurate. They all seem to agree, give or take the occasional microwave oven rebellion after a power outage. But if you had to pick the real champion of timekeeping, something so precise it could tell if your apartment was slightly closer to sea level than your neighbours, you'd be looking at an atomic clock, not just accurate to the second, not even to the millisecond. These marvels are accurate to a few billionths of a second per day. They don't just keep time, they define it. And here's where it gets beautifully weird. Even these flawless clocks, our most objective measurement of the universe's tempo, tick at different rates depending on their location. All thanks to time dilation. Let's run a simple thought experiment. You take two identical atomic clocks. One you leave on the ground floor of a building. The other, you carry it up to the top floor, maybe 30 or 40 stories high. Then you wait. After some time, you compare them. The one on the higher floor has ticked faster. You didn't touch the clocks. You didn't speed anything up. You just moved one away from Earth's gravity by a few hundred feet. That's all it takes. Less gravity, faster time. This has been experimentally confirmed many times. It's not just a lab trick. It's real physics happening right under your feet. In 2010, physicists at the National Institute of Standards and Technology, NIST, in Colorado, conducted an experiment where they raised one atomic clock by just 33 centimeters, about the height of a small dog, and it ticked faster than its sibling below. That's less than the height difference between your head and your knees, which means yes, technically, your brain is aging faster than your feet. Congratulations, you're a vertically inefficient time traveller. This gravitational time dilation is a direct result of Einstein's general theory of relativity, which tells us that time slows down in stronger gravitational fields, and the stronger the gravity, the more pronounced the effect. On Earth, we're not talking big shifts, a few nanoseconds here and there. But take this principle to extremes, and you get major divergences. Put an atomic clock on a mountain and another at sea level, and they'll disagree over time. Put one on a satellite orbiting Earth at high velocity and altitude, and now both speed and gravity are at play. It turns out orbiting clocks are fast. Between being higher in Earth's gravity and moving at significant speeds, satellite clocks diverge in measurable, predictable ways from clocks on the ground. And this isn't just academic. We rely on synchronized atomic clocks in satellites to keep everything from financial transactions to global communications and air traffic in sync. Even a tiny misalignment could throw the whole system into chaos. Historians still argue whether Christian Huygens, who designed one of the first pendulum clocks in the 1600s, ever dreamed we'd reach this level of timekeeping precision. It's unlikely. His clocks gained or lost about 15 seconds per day, which felt miraculous at the time. Fast forward a few centuries, and we can now detect the effect of you standing on a step stool. That's what makes this so fascinating. The faster our clocks become, the more relativity becomes real, not just for satellites or space stations, but for humans in everyday environments. Elevation, velocity, even shifts in Earth's gravitational field during a solar eclipse. Yes, that's a thing. Our clocks are so good, they're basically spying on spacetime itself. There's even talk among scientists of using networks of portable atomic clocks to map underground structures by detecting slight gravitational differences. It's called relativistic geodesy. Imagine scanning for caves, tunnels, or mineral deposits, not with radar or sonar, but with time. Let that sink in. We're starting to use time dilation as a geological tool. The future is now, and it's wearing very tiny, very precise watches. And these aren't just passive clocks. Modern optical lattice clocks, some of the most precise we've ever built, are so sensitive that even a small change in elevation due to the moon's gravitational pull can affect their tick rate. In other words, your position relative to a lunar tide can bend your seconds just a little. It's like the universe is constantly adjusting your personal tempo with an invisible volume knob. And these clocks can hear every flick. Of course, all of this is happening around you, invisibly. You don't feel your time stretching or compressing. There's no cinematic slow motion, no Matrix-style bullet dodging, but every tick of your life, your breath, your heartbeat, the gentle rise and fall of your chest, is happening inside a temporal field shaped by where you are, your altitude, your speed, your position on a spinning planet orbiting a star in a galaxy that's cartwheeling through space. And as you listen to this, lying still, you might wonder, what's the fastest clock in the room? Technically, it would be the one furthest from the floor. Even the slight height difference from your phone on the nightstand to your wristwatch counts. Not enough to change your bedtime, but enough for physicists to smile about. Because once you know this, you see the world differently. You realize that time isn't something you carry with you, like a suitcase. It's a field you swim through, a tempo shaped by gravity and motion. Your age is not universal. It's contextual. You're not just older today than you were yesterday. You're older in your gravitational frame, your little patch of the universe. Out there, somewhere, a photon is still racing toward Earth from the edge of space. It's been travelling for billions of years, and while it's moved at light speed, it hasn't experienced time at all. From its perspective, no time has passed. The journey is instant, and here you are, tangled in a blanket, thinking about what to eat tomorrow. Clocks, it turns out, are more than just instruments. They're mirrors, showing us how the universe bends, curves, and plays favourites. They're not keeping time, they're recording how your time unfolds, and the most precise ones, they whisper secrets about your place in the cosmic ballet, one tick at a time. You've made it this far, curled up in your cosy space-time pocket, with your clock gently ticking away at its own particular pace. But now, we're going to drift somewhere, stranger, somewhere the ticking slows so much it's practically silence. Somewhere time itself begins to freeze. Not metaphorically, not emotionally, but literally. Welcome to the edge of a black hole. Not into it, of course. We're not animals. We're just hovering respectfully outside its event horizon, like polite tourists admiring a volcano. Except this volcano eats light and breaks the laws of reality. Black holes are the ultimate gravitational flex. They're what happens when matter collapses so tightly, with so much mass packed into so little space that it warps space-time into a funnel so deep that nothing, not even light, can climb back out. And here's where it gets trippy. The stronger the gravity, the slower time passes. And a black hole's gravity is so extreme, it doesn't just slow time, it nearly stops it. Imagine you're watching a friend fall toward a black hole. From your safe distance, say, orbiting around the black hole in a sci-fi worthy spaceship, you see them descend slowly at first, then slower and slower, until they seem to freeze at the event horizon, the edge beyond which return is impossible. They never quite cross it, not to your eyes. Their motions become sluggish, their waving hand hangs mid-air, their last shout is stretched into a ghostly hum. Time dilation becomes infinite at the event horizon. From your perspective, they've entered a moment that never ends. Now switch views. From their perspective, the fall happens fast. Normal even. Gravity pulls them in, and they experience nothing particularly strange at the horizon itself. Assuming the black hole is massive enough to avoid the whole spaghettification thing, which we will absolutely revisit later, but once inside, their fate is sealed. Time and space switch roles, and moving forward in time means falling deeper inward. There's no turning back, no hovering, only in. Historians still argue whether Oppenheimer and Snyder, who first published the mathematics of black hole collapse in 1939, understood just how shocking the time implications were. Their paper sat relatively ignored for decades, mostly because the physics community wasn't ready to believe such objects could actually exist. Now, we've not only found them, we've photographed one. Or rather, we photographed its shadow, the place where light used to be. But back to the edge. The event horizon isn't a physical barrier. You could, in theory, cross it without ever noticing. There's no clang, no siren, no red neon sign flashing too late. It's just that from the outside you stop being observable. You're still there, just frozen in time as far as the rest of the universe is concerned. That's the paradox. To you, time flows normally, but to the universe, you've gone still. And here's the real kick. Black holes teach us that time isn't a universal backdrop. It's not a stage on which the universe performs. It's part of the performance. It's dynamic, flexible, and, when confronted with extreme gravity, fragile. So what happens to time inside the black hole? Brace yourself, we don't know. Once past the event horizon, all our equations go bananas. General relativity, which has served us faithfully so far, starts to collapse under its own weight. The math breaks down at the singularity, the central point where density becomes infinite, and space-time curves into a point so sharp that all physical laws vanish. And the singularity doesn't just warp time, it destroys it. There is no ticking, no flow, no before or after, just a crushing, eternal now that nothing escapes from. Some theories suggest that time doesn't even exist at the singularity, that it gets compacted into a point of zero duration, like a story that ends in the middle of a sentence and then eats the book. Others, particularly those dabbling in quantum gravity, whisper that perhaps there's something beyond that point, a bounce, a wormhole, a tunnel to another universe. But even in those ideas, time changes shape. It ceases to be what we experience and becomes something alien, twisted, incomprehensible. And that brings us to wormholes. Ah yes, the sci-fi darling. A hypothetical tunnel through space-time that could, in theory, connect distant parts of the universe, or even different points in time. Wormholes arise naturally from Einstein's equations, but so far we have no proof they exist. Still, it's fun to imagine a cosmic shortcut that lets you leap across galaxies while skipping the in-between years. But here's the rub. Even if wormholes are real, they'd still be subject to time dilation. One end near a black hole would tick slower than one in open space. Travel through it, and suddenly you're not just in a new location, you're in a new when. Time once again refuses to behave. You could use a wormhole to jump into the future if you set up one end near something with intense gravity or extreme speed, and then waited. The difference in clock rates would create a natural time offset. You walk through a doorway and emerge decades later, from your perspective, in seconds. The universe? Not so much. But going backward? Nope. The universe locks that door tight. Even the most creative theories can't quite figure out how to make time run in reverse without unleashing paradoxes so destructive they make black holes look polite. So here you are, watching time near a black hole slow to a crawl. The universe moves forward, your friend appears frozen, and somewhere deep inside that event horizon, time has stopped meaning anything at all. Here's a fringe tidbit for your sleepy brain to chew on. Some physicists believe that black holes might actually store time, that the information of everything they've swallowed is encoded not inside, but on the surface of the horizon, in some strange holographic memory bank. If that's true, then time itself, its shape, its history, might be smeared across the edge of darkness like fingerprints on a frosted window. Think about that the next time you forget your password. So yes, wormholes, black holes, frozen time, all very dramatic, but they're not fantasy. They're the logical, if uncomfortable, conclusions of the math that also powers your GPS and keeps atomic clocks honest. And more importantly, they remind you that time isn't fixed, it isn't fair, and it definitely isn't done surprising you. You're still wrapped in your own gentle timeline, far from collapsing stars and cosmic tunnels. But the knowledge is there, humming under your thoughts. Time can freeze, warp, bend, even vanish. And the ticking of your clock? It's just one version of a story that plays differently everywhere else. All right, let's leave the edge of the black hole behind. You floated long enough in infinite gravitational weirdness, and your brain deserves a little return to the relative comfort of Earth. Though I do say relative with a smirk, because as you've probably realised by now, relativity never takes a day off. Let's come back to something a bit more grounded, something a little closer to your everyday life. Time dilation you can almost feel. Yes, really. Because even in your regular gravity-laced, non-black hole-infested existence, you're moving through tiny, measurable variations in time, riding an elevator, flying on a plane, sitting on the top bunk instead of the bottom. These things all cause you to age ever so slightly differently than someone else just a few feet away. You're probably not walking around muttering, "My seconds are slipping faster than yours," but maybe you should be. You'd technically be correct, and those are the best kind of correct. Let's start simple. You step into an elevator on the ground floor, you ascend. Maybe it's your office, a hotel, one of those glass elevators in a shopping mall that makes you feel like a goldfish in a tank. As you go up, you're moving away from the Earth's centre of gravity. That means, cue dramatic music, you're aging faster than someone still standing on the first floor. Not by much. Not by enough to demand a birthday cake 0.000000001 days early, but enough that a precise atomic clock strapped to your wrist would notice. The higher you are, the less gravity you feel. Less gravity equals less time, dilation equals faster time. This means pilots, astronauts, and anyone living on the upper floors of skyscrapers are technically aging faster than people below them, by nanoseconds, microseconds, maybe milliseconds if they do it for a lifetime. Still, those slivers of time are real and permanent. Historians still argue whether the Wright brothers, in those early days of flight, ever considered that their little plane wasn't just lifting off the ground. It was lifting away from the slowest tick of time, up into the faster flow of seconds just beyond the reach of Earth's gravitational grip. Probably not. They were busy trying not to crash. But modern aviation is practically a low-key time machine. Let's say you fly from New York to Tokyo, a nice long-haul trip. Between the speed of the jet and the higher altitude, your body will age just a tiny bit more than someone who stayed on the ground. Time, in your frame, ticked faster. Conversely, if someone went into a high-speed orbit around Earth, say, aboard the International Space Station, their time would actually slow down, thanks to their incredible speed, even though they're farther from Earth's gravity. Velocity dominates, so while astronauts are higher up, which should make them age faster, their intense speed causes them to age slower than you. It's a tug-of-war between velocity-based time dilation and gravitational time dilation. Who wins? Depends on the details. In the case of the ISS, speed wins. So yes, astronauts age more slowly. This isn't theoretical anymore, it's confirmed. Remember astronaut Scott Kelly, the twin who spent a year in space while his brother Mark stayed on Earth? When Scott came back, there was measurable evidence of time dilation. He was literally milliseconds younger than he would have been had he stayed home. Sure, he also came back with weird immune system changes, a slightly longer spine, and a strong craving for Earth snacks. But let's not get distracted. You might think, okay, but I'm not an astronaut or a frequent flyer. I just go to the grocery store and binge sci-fi shows in my pajamas. Am I really aging differently from other people? Yes, technically. Even standing up and walking around the house changes your position in Earth's gravitational field. It's small, it's silly, but it's there. Your body's moving through slightly different time zones every time you climb the stairs or flop onto the couch. And it's not just you. Satellites, of course, experience constant time dilation, and it's not negligible. Without correction, GPS satellites would be off by miles within a single day. Their onboard atomic clocks run faster due to weaker gravity and slower due to their speed. The system has to apply both adjustments constantly. So in a way, even your Uber ride relies on time dilation corrections. You're living in a world built on relativistic awareness, and yet you don't feel it. You don't notice it. Your cells don't scream, "Hey, that flight just aged us more than sitting at sea level." But the clocks notice. The equations care, and slowly, subtly, those milliseconds add up. Here's a fringe tidbit to melt your mind just a little more. Your heart experiences time dilation. Blood flowing at different speeds through your arteries is moving relative to other parts of your body. On paper, yes. There's a time difference between red blood cells coursing through your aorta and those chilling in your pinky toe. Tiny, infinitesimal. But if you had a muon's lifespan, it might matter. In other words, your biology isn't exempt from relativity. Of course, none of this is perceptible to you. Your lived experience of time feels uniform. You don't age faster because you stood on your tiptoes. You don't get a time bonus for using the escalator instead of the stairs. But physics knows, and it's keeping score. In fact, time dilation has become such a routine consideration in high-level science and technology that some physicists are exploring ways to harness it, not just compensate for it. Hypothetical deep space missions could use time dilation to allow astronauts to travel further while aging less. Want to skip a century and only experience a few years yourself? Build a ship that can cruise at 99.99% the speed of light. Easy, right? Okay, easy might be optimistic. We'll get to that. But until then, you can take comfort in knowing that even in your most mundane activities, commuting, walking the dog, riding an elevator, you're living a relativistic life, a time-bent life. One shaped not by absolute seconds, but by the unique context of where you are and how you're moving. You're not stuck in a universal clock tower, you're adrift in a sea of flexible time, affected by forces so subtle you don't even know they're there. But your body, your atoms, your watch, they all respond. So next time someone says time flies, you can nod wisely and say, yes, and I did too, a little bit faster than usual. Now you're staring up at the stars, maybe through a window, maybe in your imagination, and they seem peaceful, timeless, like the sky has been frozen for centuries, unchanged since the days of pyramids and philosophers. But here's the trick. The light you see is not just light. It's time. A time machine for your eyes. Because every star, every flicker, every gentle glow up there is a story from the past. You're not seeing the universe as it is. You're seeing it as it was. And some of those stars, they're already gone, dead, exploded, collapsed into themselves, but their light is still catching up to you, making its final journey across the gulf of space. Welcome to the most poetic side of time dilation, the cosmic light show from the past. Light travels fast, about 300,000 kilometers per second, but the universe is big, like aggressively big. So even light, the universe's cosmic speed demon, takes its sweet time to reach us. The moon! Its light takes just over a second to get here. The sun? About 8 minutes. But stars? Entire galaxies? Thousands, millions, even billions of years. Let's say you're looking at the Andromeda Galaxy tonight. It's our closest galactic neighbour, a swirling collection of 1 trillion stars about 2.5 million light-years away. That means the glow reaching your retinas right now, those ancient photons, started their journey long before Homo sapiens existed. You're not seeing Andromeda as it is. You're seeing it as it was 2.5 million years ago, when early humans were still arguing over how to hold a stick. And it gets weirder. Let's turn our gaze toward the Sombrero Galaxy, about 29 million light-years away. The light reaching you from that celestial hat was already halfway through space when the dinosaurs were wiping out. Even the stars in your own galaxy aren't immune. The bright blue Rigel in Orion, about 860 light-years away. That star could have popped like a champagne cork in the Renaissance, and we'd still be waiting to hear about it. This isn't dramatic license. It's how the universe works. Light takes time, and the farther you look, the older the images become. Telescopes. They're not just cameras, they're time machines. The Hubble Space Telescope has shown us galaxies forming billions of years ago, and its successor, the James Webb Space Telescope, is now gazing even deeper, into times before galaxies as we know them even fully existed. But why does this matter in a story about time dilation? Because it means we can see time dilation happening with our own eyes. Let's look at one of our favourite cosmic phenomena, supernovae. These are the dramatic deaths of massive stars, where a single point of light outshines an entire galaxy for weeks. When we observe supernovae from distant galaxies, we notice something peculiar. Their explosions seem to unfold slower than they should. Their brightening and fading stretch out. The entire light curve gets dragged, like someone slowed the footage down in post-production. And that's not just because of distance. That's time dilation in action, on a cosmic scale. As light travels through the expanding universe, the very space it's moving through is stretching. And that stretch dilates time. An event that took 20 days to unfold in its original galaxy might take 40 or more to appear from our perspective. It's not just slower light, it's slowed time. Historians still argue whether early astronomers had any real sense of this delay. Babylonian star charts, brilliant, accurate, but they assumed a fixed sky. No idea that they were watching ancient light drift through the heavens. It wasn't until the 20th century, when we measured redshifts, clocked cosmic expansion, and started cataloguing supernova with real precision, that we realised the universe isn't just far away, it's stuck in a time delay. This has huge implications, because it means when we look into the sky, we aren't just seeing stars, we're seeing stretched moments. We're watching the universe move in slow motion, not because it's lazy, but because space itself is pulling time apart. You can see this vividly in quasar observations, those bright distant cores of young galaxies with black holes guzzling matter like cosmic vacuums. Some of them are billions of light years away, and we've watched their flickers stretch and sway, their time signatures literally warped by the vast expansion of the universe between us. Think about that. Something flashes near a black hole in a galaxy that formed shortly after the Big Bang. That light races across time, gets redshifted, slowed, distorted, and finally lands on your telescope lens, or your eyeball. It has spent its entire existence travelling to meet you, and for some photons, that trip began before Earth existed. We're walking around, scrolling social media, making lunch, while the messages of the cosmos arrive like delayed postcards from a civilization that doesn't even remember it sent them. You don't need a spaceship to see time dilation, you just need to look up. Even the colour of starlight betrays it. Blue stars are newer, hotter, often closer. Redder stars? Older, further, their light stretched by the expanding universe. This is called redshift, and it's not just a Doppler effect, though that's part of it. It's a signature of space stretching, of time elongating, of the fabric of the cosmos pulling itself thinner as it grows. It's easy to forget, lying under the stars, that you're being lied to gently by every twinkle. Nothing is happening up there as it seems. You're watching memories, ghosts, ancient flame flickers, some from stars long dead and gone. But that's the charm, isn't it? You're connected to something much older than you. You're seeing history in the raw. The stars don't care that you had a bad day or forgot to do the laundry. They're sending you signals across time, inviting you to feel a bit smaller and a bit more timeless every time you look up. So next time you glance at the night sky and wonder what's happening up there, remember, it already did. Long ago. You're just now catching the afterglow. And your pupils? They're tiny telescopes catching the oldest light in the universe. So you're lying there, eyes closed, perhaps still picturing that night sky we talked about, blanketed in stars, galaxies, and the ghost light of cosmic history. But what if I told you the biggest event in the universe's history, the grand opening act of everything, is still happening right now? Because in a way that defies all bedtime logic, the Big Bang is still unfolding, and you're living in its echo. Let's rewind. Not just to the Renaissance or the dinosaurs or even the formation of Earth, but all the way back, 13.8 billion years ago, to a moment so small and hot and dense that space and time were indistinguishable. No stars, no atoms, no before, just an expanding ball of energy that eventually cooled into the universe we know. That was the Big Bang, a name that frankly is misleading. There wasn't a bang, there wasn't even a place for it to bang in. Space itself was born in that moment, along with time. It didn't explode into a pre-existing void. It created the void and then filled it. But here's the kicker. Because of time dilation on a cosmic scale, the early universe hasn't finished arriving. You're still receiving the light, the literal radiation, from that primal moment, and it's taking its time. Ever heard of the cosmic microwave background? That faint afterglow, cooled to just a few degrees above absolute zero, is the ancient light from the moment the universe became transparent, about 380,000 years after the Big Bang. Before that, photons were trapped in a fog of plasma. But once things cooled enough, the fog lifted and light was free to travel, and it's still travelling. To you. That's right. Right now, photons from that moment are still arriving, still gently tapping the antennas of space telescopes, still softly hissing through your TV static if you remember those old analog screens. You're literally bathed in ancient light, stretched by billions of years of expansion until it's no longer visible. Just a warm whisper in the microwave spectrum. And here's where it gets weird. Because of time dilation caused by the universe's expansion, what we see as then is stretched across billions of years. That first flicker of transparency is smeared across our present like cosmic peanut butter. The event happened all at once back then, but from your perspective, it's still happening, still arriving, still visible in every direction. You're the center of a sphere, not the physical center of the universe, but the center of your own observable bubble. Light has been traveling towards you since the beginning of time, and your point of view creates a spherical shell of visibility. The farther out you look, the farther back in time you see. And at the edge? That soft hiss of microwaves, the cosmic microwave background, CMB, is the edge of time as we know it. Now don't confuse this with the edge of the universe. We don't know where or if that exists. The CMB is just the edge of what we can see. Beyond that, the universe keeps going, expanding, hiding its secrets behind a curtain of ancient radiation we can't see through, at least not yet. Historians still argue whether the term Big Bang does this concept justice. Fred Hoyle coined it sarcastically in a radio interview, and the name stuck. But what it describes isn't a firework. It's a time-warped birth, with its light slowed and stretched across the eons, reaching you piece by piece. And it's still coming. Even now, telescopes like Planck and WMAP study the texture of that radiation. The slight fluctuations, tiny wrinkles in the temperature of the CMB are like baby pictures of the universe. Not blurry snapshots, but finely detailed scans. These patterns reveal the seeds of every galaxy, every star, every puff of gas that would one day form planets and brains and poetry. And those wrinkles, they're also affected by time dilation. Photons from denser regions, from stronger gravitational fields, have their frequencies stretched more than those from emptier zones. It's called the Sachs-Wolf effect. And yes, it's another reminder that even the earliest photons couldn't escape the clutch of gravity on their way to you. You're watching ancient light that has been bent, stretched, slowed, redshifted, warped by gravity wells and cosmic expansion before it politely knocked on your detectors, and we're still using it to decode the universe. When you hear astronomers say they're looking at early galaxies, they mean light that's taken most of cosmic history to arrive. And as they look deeper with tools like the James Webb Space Telescope, they're seeing stranger things, galaxies that appear more mature than they should be, formed too early, too big, too bright. This isn't just a curiosity. It may be a sign that our model of time dilation in the early universe still has gaps. Some scientists propose tweaks to inflation theory, while others wonder if dark energy, yes, the weird stuff accelerating the universe's expansion, could also be warping time in ways we haven't accounted for. Which brings us to another unsettling thought. We don't experience cosmic time the same way the universe does. There's a concept called conformal time, a mathematical transformation that shows how the entire history of the universe could, in a certain view, be compressed into a finite, manageable shape. In this version of events, the Big Bang is not just a point in the past, it's the boundary of all possible time, and the present, just another wrinkle on a curved page. So while you're here, brushing your teeth, wondering why cereal tastes better at night, the universe is still mid-birth from a certain perspective. You're a creature made of ancient atoms, watching the aftershocks of creation ripple by in stretched-out, time-dilated waves. And your moment, your now, is stitched into the expanding fabric of space-time like a single bead on a balloon that never stops inflating. The Big Bang didn't happen then. It's happening still from your point of view. Every starlight you see, every supernova light curve, every cosmic echo is a glimpse at how the past isn't gone. It's just out there, still catching up. So if you ever feel late to the party, just remember, you're living inside a birthday that hasn't finished singing yet. You're still drifting, mentally or literally, beneath a universe that's stretching, glowing, and quietly ignoring your need for a bedtime routine. But don't worry, you're in good company, because the universe isn't just expanding, it's humming. Humming in a long, low note you can't hear, with every galaxy slipping away like sirens fading down a cosmic highway. And that sound, that hum, it's not actual audio. It's the redshift, a kind of Doppler effect for light. And it's the clearest sign that the very fabric of space is pulling apart, and with it, time is being stretched like taffy. So let's talk about redshift, space's Doppler effect, and why it means we see the universe not just moving away, but aging differently than we are. Start here. Imagine an ambulance speeding toward you. The siren's pitch is high. As it passes and drives away, the pitch drops. That's the Doppler effect, the compression and stretching of sound waves due to motion. It's basic physics, the kind that makes race cars sound like angry bees when they fly past you. Now replace sound with light. If a star or galaxy is moving toward you, its light gets compressed, shifting toward the blue end of the spectrum, blue shift. If it's moving away, the light stretches out, and its colour shifts toward red. That's redshift. But when we look out at the universe, we see redshift everywhere. Not just in galaxies moving away because of local motion, but in galaxies whose light is being stretched by the expansion of space itself. It's not that they're speeding away like rockets. It's that space between us is growing. This type of redshift, called cosmological redshift, is different from the Doppler kind. It's not a galaxy flying away through space. It's space itself getting longer between you and the galaxy, stretching the light as it travels toward you. And here's the crucial part. This stretching of light is also a stretching of time. When we watch a distant supernova, we're not just seeing its light redshifted, we're seeing the explosion happen slower. The pulse of brightness and the fading embers stretch out. Its time gets pulled, dilated, smeared across your telescope's detectors. From your perspective, the event is unfolding in slow motion. It's not a trick. It's real. It's how the universe delivers its messages. So if you're ever tempted to call a distant galaxy ancient, remember, you're still watching its present, just a very redshifted, time-dilated version of it. Its now is tangled up with your past, and neither of you is seeing the full picture. It's like trying to watch someone jog across a rubber band that's being stretched while they move. You think they're slowing down. But the truth is, the track is lengthening beneath them, and it's happening in every direction. Look left, redshift. Look right, redshift. Up, down, anywhere your telescope points. The universe is slipping away, every photon a tiny red flag flapping in retreat. But not everything redshifts equally. Galaxies closer to us shift less. The farther away they are, the more their light is stretched. That gives us a beautiful little cosmic ruler. Astronomers use redshift as a way to measure distance, with higher redshifts pointing to deeper time and space. It's like the farther you look, the older and slower things become, not because they're sluggish, but because their reality is unfolding under a different tempo. Now here comes the weird part. The expansion of the universe is accelerating. That means distant galaxies aren't just drifting, they're speeding up, pushed apart by something we call dark energy. We don't know what it is, we don't know how it works, but we know it's making space grow faster over time. And this acceleration means that some galaxies are now moving away from us faster than the speed of light. Wait, what? Yes, it's allowed. Because nothing is moving through space faster than light. Space itself is expanding, and that expansion isn't bound by the speed limit of relativity. So there are galaxies whose light, right now, will never reach us. They're already beyond our cosmic horizon, slipping permanently out of view like ships vanishing into fog, and with them, their time, their future events, their supernovae, their galaxy mergers, their alien soap operas, if they have those, will never be part of our story. Time, for them, is simply gone from our experience. Historians still argue whether Hubble, yes, that Hubble, understood what he was really seeing when he plotted the relationship between galaxy distance and redshift in the 1920s. He was observing the fingerprints of an expanding universe, yes, but also the beginning of an idea so unsettling it would take decades to truly absorb, that the cosmos has a time structure that isn't shared, that the universe we observe is fundamentally distorted by distance. And here's a fun fringe idea to sprinkle on your sleepy brain. Some physicists believe that redshift might not just be about space stretching, it might be telling us something deeper about the nature of time itself. That time at a cosmic scale might emerge differently depending on your frame of reference in an expanding curved universe, which frankly feels like something only a galaxy could understand. Meanwhile, here on Earth, your experience of time is tied to blue skies, ticking clocks, and microwave dinners. But when you look out at the universe, you're seeing a completely different rhythm. A longer, slower, dragged-out performance that began billions of years ago and is still playing, only at half speed, or quarter speed, or less, depending on how far you look. You are immersed in a cosmic delay, and that delay isn't passive, it's information. Redshift tells us not just that galaxies are far away, but how time is flowing for them, and how it's diverging from your own. And here's a poetic little final note. Every redshifted photon you catch was once a vibrant, energetic burst of light. A blue-white blast, a sharp ultraviolet edge. And now, it arrives at your telescope like a tired traveller, red, slow, weary from the journey. Light loses nothing in a vacuum, but space stretches it out, cools it down, makes it old. So the next time you think of light as instant or perfect, think again. It can be aged, bent, slowed. Redshift isn't just distance, it's the echo of time, written in the colour of the stars. You're still here, nestled in your quiet space, thoughts drifting somewhere between science and sleep. The universe, meanwhile, continues doing what it does best, expanding, shifting, pulling time apart. But now it's time to go one layer deeper, to tug gently at the one thread that still might be clinging to the idea that there's such a thing as now. Because if redshift taught us that the stars are lying about the present, then this part will seal the deal. Here's the truth, whispered gently. Now doesn't exist, not universally. There is no shared moment, no cosmic group chat where every atom checks in at the same second. In the grand scale of the universe, the illusion of simultaneity breaks down completely. Welcome to the illusion of now in space. It's something you feel intuitively here on Earth. You look at your friend across the room and assume you're both existing in the same present. Your conversation feels instantaneous. You high-five and it all syncs up. That's because the distances are tiny and the speed of light is fast. Light bounces between you almost instantly, so your brains stitch together a working model of simultaneity. But stretch that distance a little, say, to the moon, and things begin to wobble. It takes light 1.3 seconds to reach us from the moon. That means a message sent from there doesn't arrive now. It arrives later, even if later is only by a second. Now imagine a spaceship hovering around Saturn. Light takes over an hour to get from there to here. Any video call? Unbelievably awkward. And yet your mind still wants to assign a now to that distant place. As if Saturn has a clock ticking in step with yours. It doesn't. Take that further. Imagine a planet orbiting a star 500 light-years away. What is happening there right now? You don't know. You can't know. Because the light reaching your eyes from that star left half a millennium ago. That world's present is forever hidden from your view. All you see is the past. And all they'd see, if they pointed a telescope at Earth, would be jousting knights and questionable hygiene practices. This isn't just about slow communication, it's about the structure of space-time itself. Einstein's theory of special relativity shattered the idea of a shared, objective now. Instead, he showed that simultaneity is relative. It depends entirely on your frame of reference. Two events that happen at the same time in one person's viewpoint may happen at completely different times for someone else moving at a different speed or in a different place. Let that sink in. There's no such thing as a universal clock ticking the same for everyone. The moment you're experiencing as now could be someone else's distant past or their future. Depending on motion and location, your timeline is yours alone. Historians still argue whether even Einstein fully grasped the emotional consequences of this. Physics doesn't mind, it's cold and logical. But for you, it's a little weird, a little unsettling. The realization that your experience of time is not globally shared, that no one in the entire universe sees things unfolding in the exact same order you do. Think of it like this. Space-time isn't a grid. It's a flexible, four-dimensional fabric. Your position and velocity tilt that fabric. You experience slices of space-time based on your movement and gravity, and those slices define what you call now. Change your speed? Your now changes too. This leads to a strange implication. In some frames of reference, your future is already happening, and in others, it hasn't yet begun. This isn't time travel, it's relativity. And while it doesn't let you cheat causality or skip ahead with a time machine, it does mean that your concept of the present is entirely local, contextual, fragmented. So when you gaze at a star and think, I wonder what's happening there right now, the universe shrugs and says, depends on who you ask. The farther out you go, the less now means anything. It's one of the reasons modern cosmology avoids speaking in terms of current events for distant objects. Instead, scientists use redshift, light years, and cosmic time to communicate when something happened in a shared, agreed-upon model, usually based on the time since the Big Bang, not any local clock. Because simultaneity? Gone! Not a thing. Never was. And here's a fringe gem for you. Some physicists propose that this lack of simultaneity isn't just a byproduct of relativity. It might actually emerge from deeper laws, tied to the fundamental limits of information, that nothing can be shared instantly, and therefore no true present can span the cosmos. Time becomes an emergent property, not a baseline, a side effect of being local and conscious and limited by light speed. It's beautiful and a little lonely. You exist in your own causal bubble, the part of the universe you can interact with, shaped by the speed of light and your place in space-time. Everything else, it might as well be a dream, a photograph, a rumour from another century, and yet it's not a tragedy. It's a kind of intimacy. Because while now can't be shared across galaxies, it's real here, with you, with your surroundings, with the people in your gravitational and motion frame, your cat, probably sharing your now, at least until she knocks something off the counter and shifts the timeline forever. So what do we do with this knowledge? We embrace it. We accept that the universe is stitched together not by a single timeline, but by billions of overlapping ones, each one local, each one valid, all flowing at different speeds, under different rules, shaped by motion and mass. You're not synced with the stars. You never were, but you're part of the same story, reading a different page maybe, but from the same cosmic book. And now you rest. You let the weight of these thoughts soften. You let go of the illusion of universal time and sink into your own gentle stream of seconds, yours, unique, unrepeatable. Time isn't absolute, but it's real, right here, right now, for you. You're drifting now. Maybe your breathing has slowed. Maybe your thoughts are tangled somewhere between dreams and equations. But before you slip too far, there's one more thread to tug gently. Perhaps the most tempting, the most whispered about question in all of physics. Can you travel into the future? Can you go back to the past? Because if time is flexible, if clocks can tick faster or slower, if simultaneity is shattered, if events stretch and compress, then surely we can hack the system, right? Find a shortcut, build a machine, take a peek at what's coming next, or revisit something that's already passed. The answer, you can go forward. That part is real, proven, done. But going back, that's where physics slams the door and bolts it shut. Let's start with the forward jump. Time travel to the future is not only possible, it's already happened, just in small doses. We've seen it in particle accelerators, with high-speed particles experiencing time much more slowly than those at rest. We've seen it with astronauts who come back to Earth having aged a little less than their Earthbound counterparts. Remember Scott Kelly and his twin? Milliseconds younger after nearly a year in space. It's tiny, but it's real. If you really wanted to jump forward in time in a big, noticeable way, you'd need one of two things: extreme speed or extreme gravity. Let's say you build a spaceship that can travel at 99.999% the speed of light. You take a 10-year round trip. For you, only a year passes. When you return, Earth has aged a decade. That's time travel. No flux capacitor required, just special relativity and enough fuel to bankrupt a small planet. Or imagine you build a colony orbiting just outside the event horizon of a massive black hole. The gravity is so intense that time near the hole passes much more slowly than it does elsewhere. You live a peaceful year in orbit. Far away, centuries pass. You come back to a world that's aged far beyond your own body. Another time leap. General relativity doing its spooky thing again. Historians still argue whether H.G. Wells, when he wrote The Time Machine in 1895, anticipated that time travel forward would actually turn out to be easier, at least theoretically, than going back. Wells imagined a lever and a brass chair. Einstein gave us equations and impossible fuel demands. Slightly less steampunk, but undeniably more accurate. But what about the real question? Can you go back? That's where physics starts to look uncomfortable, like a party guest who just realised someone asked them to explain their ex. Backwards time travel introduces problems, big ones, namely paradoxes. Let's say you go back in time, you meet your past self, or you stop your grandparents from meeting, or you warn the world about a disaster that hasn't happened yet. All of these ideas create logical loops, the infamous grandfather paradox. If you change the past, how do you explain the future you came from? Physics doesn't like paradoxes. They make equations sad. Now, there are solutions in general relativity that describe closed time-like curves, paths through space-time that loop back on themselves. You can find them in extreme models involving rotating universes, like Gödel's solution, or wormholes stabilized by exotic matter. In these scenarios, time loops could exist, in theory. But here's the catch. They require conditions we've never observed, like negative energy densities or faster-than-light travel, and even if we did find them, they might be instantly destroyed by feedback effects or protected by some yet unknown law of chronology protection. That's an actual idea, by the way. Stephen Hawking proposed the chronology protection conjecture, which basically says nature won't let time travel to the past happen because it would break causality. It's like the universe has a built-in bouncer at the back door, just in case someone tries to sneak in wearing a paradox. And if you're hoping quantum physics will save the day, well, not quite. Quantum mechanics allows for all kinds of strange things, particles being in two places at once, entanglement, uncertainty, but it doesn't give you a time machine. Some interpretations suggest the possibility of branching timelines, every choice or event spawning a new universe where different outcomes unfold. In this model, maybe you could go back, but only to a different version of the past, one where you exist as a duplicate and your actions don't change your own timeline, just someone else's, which feels less like time travel and more like cosmic tourism. Here's a fringe thought to lull you into sleep-adjacent confusion. What if the reason we don't see time travelers is because they'd arrive in a different timeline altogether? One that has no memory of their visit. Or worse, one where their arrival deletes the version of events they intended to change. No paradox, just narrative heartbreak. Either way, the consensus is clear. You can go forward. You already are every second at your own unique speed. You can speed it up by flying faster or living near something very dense, but going backward? Physics as we know it just won't allow it, at least not without breaking everything. So for now, your relationship with time is strictly one way, forward motion only. You can stretch it, slow it, loop it weirdly under intense gravity, but you can't flip it in reverse, and maybe that's okay, because moving forward is what makes everything meaningful. The fact that moments pass only once is what gives them weight. If you could loop back, would you ever really move on? Would you let anything matter? You're already a time traveller, you're just on the slow setting, aging in your personal frame, sliding along a curve of space-time sculpted by mass and motion. No need to punch a button or find a portal. You're already in the machine, and while the past is unreachable, it's not gone. It's still out there in a way, baked into the fabric of space-time, encoded in ancient light, whispered in the redshift of galaxies. Your job? Just keep going, forward. You stretch your arms a little, shift under the covers, and maybe, just maybe, you start to feel the ticking of time not as a rush or a blur, but as something a bit more flexible, more forgiving. You're not sprinting toward old age. You're riding a soft, curved path through a universe that's more than happy to let you take your time. And if you ever needed proof that real time travel already exists, even if it's not as dramatic as a phone booth or a DeLorean, look no further than a little up. To space. Because right now there are people orbiting the Earth who are younger than they should be. Astronauts. Not by much. Fractions of a second. But still, they've aged just a little more slowly than you since launch. Not through magic, not through suspended animation, just physics. Specifically time dilation. They are aging differently because of where and how fast they're moving. Let's take a closer look. The International Space Station orbits Earth at roughly 28,000 kilometers per hour, or about 17,500 miles per hour. It zooms around the planet every 90 minutes, slicing through the upper edge of Earth's gravitational influence. And that speed? It's enough to invoke special relativity. As we've learned, The faster you move through space, the slower you move through time. Now combine that with the station's altitude, about 400 kilometers above sea level, which means astronauts are in slightly weaker gravity than we are here on the surface. And weaker gravity means, thanks to general relativity, time should tick a little faster for them. So which wins? Surprise, it's the speed. Yes, astronauts on the ice age slightly more slowly than we do here on Earth. The velocity-induced time dilation outweighs the gravitational time boost. The net result is that for every 6 months spent in orbit, they age by about 0.007 seconds less than someone on the ground. That might not sound like much, but it's measurable and cumulative. Over many missions, astronauts are slowly becoming the youngest people of their age cohort. Historians still argue whether Yuri Gagarin, the first human in space, technically aged less than someone born the same day who never left the ground. The answer is yes, by an absolutely microscopic amount. But physics doesn't care how small, it only cares that it's real. And this is where things get even more interesting. Because if you extended the concept, if you kept someone in orbit for decades, or better yet, built a ship capable of reaching a significant fraction of light speed, you'd begin to see the time divergence grow. Suddenly it's not milliseconds, it's years, maybe decades. Imagine a future astronaut, let's call her Mira, who embarks on a relativistic mission to a nearby star system. She travels at 99.9% the speed of light. For her, the round trip takes 10 years. But when she returns, Earth has aged hundreds. Her friends are gone, her family is history, her culture, her language, even the snack she liked. All distant memories. She hasn't aged a day past 40. Earth has moved on. And that's the truth about time dilation. It's not about stopping time, it's not about beating death. It's about changing your relationship with time, experiencing less of it than others, becoming a witness to fast-forwarded civilizations. And here's the thing, we already have the evidence. Not just in theory, not just in simulation, but in real people. Like Sergei Avdeyev, a Russian cosmonaut who spent 747 days aboard the Mir space station. When he returned to Earth, he was 0.02 seconds younger than he would have been had he stayed. That's 20 milliseconds of time travel. Not enough to notice, not enough to tell anyone about at a party, unless that party is full of physicists, but still, a real effect. There's something poetic about that you can escape time, if only a little. That gravity and speed are tools, not prisons. That we've already started building the first generation of time travellers, whether or not they get the fanfare. And they don't just age slower, they experience reality differently. Astronauts aboard the ISS see 16 sunrises and 16 sunsets every single day. Their clocks tick differently. Their orbit forces them to schedule life around shifted cycles. Their days and nights blur. Their perception of normal time already warped. And this affects more than their bodies. It affects how they think, how they sleep, how they interpret time passing at all. Some astronauts describe time on the station as elastic. Days feel both long and short, repetitive and unique. It's like living inside a long-haul airplane where every moment feels slightly outside your native clock. That's the human experience of relativity. Not equations, but feelings. The awareness that time is not just passing differently, but being lived differently. Here's a strange little fact. On the Moon, time ticks faster than on Earth. It's farther from Earth's gravity, and the Moon's own gravity is weaker. So if you were to live there for a while, say, in one of those futuristic lava tube habitats, your biological clock would beat just a little ahead of your friends back home. Same goes for Mars. Live there long enough, and you're biologically older than you would have been had you stayed on Earth. But you've also experienced time faster because of weaker gravity and a slightly different orbital dynamic. The universe isn't synchronized. It never was. And here's the dreamy kicker. Some scientists have proposed using time dilation as a tool for long-term preservation, a way to skip ahead without living through every moment. Want to see what Earth looks like in 10,000 years? Build a ship that loops around a black hole, where time is practically paused. Live a few days, return home, say hi to the future, you'd be younger, Earth would be transformed, and your own species might not recognize you. But you would have aged slower, truly and irrevocably, like all astronauts do, just by a tiny bit more. So yes, astronauts are younger than you. Every time they launch, they borrow a few seconds from the universe, and they pay it back in memory, in motion, in stories. Time dilation isn't a dream, it's real, it's measurable, and the humans doing it? They're already out there, floating above your head, skipping ever so slightly through the river of time. By now, you've time-travelled vicariously through astronauts, satellites, and the slow stretch of the cosmos itself. But you're still here, safely wrapped up in your own little gravitational nest, moving through time at a pace that feels ordinary, even though it isn't. But what if you zoomed in, really zoomed in, all the way down to the particle level, those subatomic flecks of matter that make up your bones, your breath, your favourite blanket? Because even here, in the strange invisible dance of quantum particles, time dilation makes an appearance. In fact, it was here, among the tiniest building blocks of the universe, that we first saw time's grip start to loosen. Welcome to the world of chrononauts of the particle realm. It starts with a particle called the muon, a distant cousin of the electron, heavier, shorter-lived, and always in a hurry. When at rest, a muon lives for about 2.2 microseconds. That's 2 millionths of a second. Barely time to blink, even if you're a hummingbird. But send a muon flying near the speed of light, and something magical happens. It survives, longer than it should. Not because it gets stronger or tougher, but because its time stretches. From our perspective, the muon is living in slow motion. This isn't theoretical. We see it every day in particle accelerators, and even in Earth's atmosphere, where cosmic rays strike particles high above us, creating muons that rain down toward the surface. These muons should decay before reaching the ground, if they were obeying normal slow-moving time. But they don't. Because they're moving fast, and in their frame of reference, less time passes before they reach us. This was one of the first experimental confirmations of special relativity. Scientists knew the math, but when they detected far more moans at ground level than expected, the answer wasn't faulty equipment. It was Einstein's equations made real. Time isn't absolute, and particles know it better than anyone. Historians still argue whether the first physicists expected to find such a clear demonstration of time dilation in cosmic rays. But nature is often more cooperative and more surprising than expected, and it gets better. In particle accelerators like CERN's Large Hadron Collider, protons are spun around a circular tunnel at 99.9999991% the speed of light. At that speed, time for those protons slows down so much that if you were somehow able to hitch a ride with them, you'd experience mere microseconds during what seems like minutes to the scientists watching from Earth. Tiny chrononauts, riding the bleeding edge of reality. It's not just muons. Other unstable particles, pions, kaons, and even B-mesons, live longer when accelerated. Entire branches of experimental physics depend on this fact. We couldn't study these particles effectively if we didn't take their time dilation into account. Their fleeting lives become noticeably longer when they move faster, and this isn't just about confirming relativity, it's also about precision. The more accurately we measure a particle's decay time, the better we understand the forces acting on it, and we're measuring these time distortions down to nanoseconds and picoseconds, all with incredible agreement between theory and observation. Time, it turns out, bends even for the smallest things, even when those things are smaller than a single atom. But what's really fascinating is how this scaling of time isn't just a trick of the math. These particles experience their full lives, however long that may be, in their own frame of reference. A muon doesn't know it's aging slowly to us. It lives its little muon life, ticking along perfectly normally from its point of view, just like you, just like astronauts, just like galaxies. Time dilation isn't a glitch in the system, it's the system itself. There's even a tiny but delightful fringe idea floating around in some physics circles. What if these particle chrononauts can teach us something about the direction of time itself? You see, in quantum mechanics, many processes are time symmetric. That means they work just as well forwards as backwards. There's no clear arrow of time baked into the math. But in certain particle decays, especially involving kaons and b-mesons, we see a slight preference, a kind of time asymmetry. They decay in ways that aren't perfectly reversible. This leads to one of the greatest open questions in physics. Why does time move forward? We experience time as a flowing river, from past to present to future. But the fundamental equations of nature don't seem to care. They're reversible. So where does that sense of forward motion come from? Some physicists suspect it's related to entropy, the tendency for systems to move toward disorder. Others think it's about cosmological boundary conditions, how the universe began in a low entropy state and has been unwinding ever since. But particles might offer a clue in their subtle, measurable preference for one time direction over the other. Could it be that the tiniest chrononauts of our universe carry the memory of the Big Bang's initial conditions? That every decay, every flicker of asymmetry is a soft whisper of the first clock ticking? No one knows, not yet. But what we do know is that time dilation isn't some rare, exotic thing. It's universal. It happens to you, to astronauts, to clocks, to particles. It scales up and down, from intergalactic to subatomic, touching everything that moves. You live in a sea of time gradients, most too small to notice, but always there. And maybe the best part, the particles don't resist it. They don't try to reverse it. They simply live their stretched little lives, gliding along whatever timeline the universe assigns them. Which is kind of beautiful, isn't it? You don't have to travel at near light speed, you don't have to orbit a black hole. Every second you live is part of a much larger symphony of time, layered and interwoven, across scales you can't see but are always dancing through. So sleep easy tonight, knowing your atoms were once particles moving at relativistic speeds, that their cousins still race through the upper atmosphere, defying decay through sheer momentum. That even the universe's tiniest citizens are, just like you, time travellers. Some nights you lie awake staring at the ceiling, wondering how time slips away so quietly, how Monday turns into Thursday without warning, how birthdays sneak up on you, how your reflection somehow seems to be aging faster than your memories. But here's a question that might gently curl around your thoughts as you drift towards sleep. Are we aging too fast? It feels like a dramatic question, maybe even a little existential. But in the context of time dilation, real, measurable, unrelenting time dilation, it's not just philosophy, it's physics. Because compared to the cosmos, your life is a blink, and that's not an exaggeration. The stars above you, the galaxies beyond them, even the tiny red dwarfs that hum along in cosmic obscurity, they age at a pace that makes human time look frantic, rushed, anxious. It's as if your clock is in a hurry while the universe sips tea in slow motion. Let's consider a star like Proxima Centauri, the closest known star to our Sun. It's a small, cool red dwarf, dim and faint, barely visible without a telescope. But it's got one big advantage over you. It's in no rush. Its lifespan, somewhere around 4 trillion years. Yes, trillion, with a T. Meanwhile, the average human gets, 80, 90 years? 100 if you're lucky and very hydrated. Red dwarfs like Proxima Centauri burn fuel slowly. Their fusion is a gentle simmer, not a roaring bonfire like our Sun. And because of that, they age ridiculously slowly. They are the great-grandparents of the future. Time stretches long for them not just in perception, but in endurance. The universe could collapse back into itself before some of these stars finish their life stories. Now imagine how strange our timeline must look from their perspective. If Proxima Centauri had consciousness, if it could look at Earth, it would see civilizations rise and fall in what feels like minutes. empires would appear and vanish between stellar heartbeats. Our wars, our triumphs, our TikTok trends, gone in an instant. That's what it means to live fast in a slow universe. We are bursts of complexity in a cosmos that drifts through eternity at a different tempo. It's not that time is cheating us. It's just that we're playing on a different speed setting, and it's not just stars that make us look hurried. Consider pulsars, collapsed neutron stars that spin hundreds of times per second. They're ticking clocks of unimaginable precision. Some pulse with such regularity that we use them to measure time across galactic distances. But even they, dense as collapsed cities, endure millions of years, far outlasting entire species, or black holes, those quiet cosmic voids that stretch time to the breaking point. Some black holes may persist forever, or at least until the universe stops expanding if it ever does. Time around them slows to a crawl. Near them, a minute for you could be 1,000 years elsewhere. So when we ask if we're aging too fast, the answer from the cosmos is a soft, amused nod. Yes, compared to almost everything else, you are sprinting. But before you feel cheated, let's reframe it. Your time is intense. It's concentrated. A lot happens in a human century. Civilizations, technologies, worldviews all flip in a single lifetime. Your experience is rich in a way most cosmic entities will never know. You may burn fast, but you burn brightly. And there's another layer to this. Your position in gravity. You're near Earth, deep in a gravitational well, which means, according to general relativity, you're aging slightly slower than someone farther out in space. So ironically, even though your life feels short, your personal time is a little stretched compared to someone far from Earth's mass. But if you really want to slow down, you'd have to change everything. Go live near a massive planet, or build a home just outside a black hole's event horizon. Your time would crawl. But would it feel like a longer life? Probably not. Time dilation is external. From your perspective, time would feel normal. It's only when compared to the rest of the universe that you'd see a difference. Your life would still feel like a century. It's just that the world outside might spin through millennia while you age your same short arc. So maybe that's the more haunting truth. You can't really feel time dilation. You just are it. You're living it every second, shaped by speed and gravity and scale, without noticing how different your passage of time is from the rest of existence. But that's not a flaw. That's a feature. Because your fast-paced timeline is the reason you feel wonder, urgency, passion, hope. It's the reason a sunrise can feel sacred, or a glance can matter, or a laugh can stay with you for years. The shortness makes it meaningful. Still, it's wild to think that if aliens exist, somewhere out there orbiting a slow-burning star in a low-gravity system, they might live on completely different timescales. What we experience in decades, they might experience in days or centuries. They might view humans as mayflies, beautiful, bright, but bewilderingly brief. And if they ever visit, we'd be long gone by the time their ships arrived. You can't outlast the stars, you can't outlive black holes, but maybe you can do something they never will. Feel time, be aware of it, experience its weight, its flow, its loss, its beauty. Maybe that's what consciousness is, a way to taste the seconds as they pass. You're not aging too fast, so you're just tuned to a different rhythm, one that gives you urgency, yes, but also awareness. You know your clock is ticking, and that makes every moment more valuable, every breath more deliberate, every whisper of time more intimate. So tonight, as the stars keep their slow vigil above you, know this: you may not last as long, but in the story of time, you are a moment that mattered. You've heard it before, that ticking time bomb metaphor, usually in movies with dramatic countdowns and sweating protagonists who always manage to defuse something with 1 second left. But what if I told you the universe might have its own timer? One you can't see, one that doesn't blink red, one that might already be counting down or up to something big. Because as we talk about time dilation and aging stars and cosmic calendars, it's time to bring in the most ominous twist of all. What if the universe's time runs out? let's get something straight. The universe has a history, yes, but it also might have an endgame. And it's not just one neat, tidy theory. There are several competing predictions, and none of them are particularly cozy. First, let's revisit the expansion. Ever since the Big Bang, the universe has been stretching out like a freshly laundered bedsheet. Galaxies moving away, redshifts growing, distances expanding. But that expansion isn't slowing down. It's accelerating. Enter dark energy, the mysterious force responsible for speeding up this cosmic expansion. We don't know what it is, we don't know why it exists, but it's there. It's roughly 70% of the universe's energy content, and it's pushing space apart more and more with every passing moment. And if it keeps doing that, forever? We get a doomsday scenario charmingly called the Big Freeze. This isn't a sudden apocalypse, it's a slow fade out. Galaxies get further and further apart, stars die and aren't replaced. Black holes eventually evaporate via Hawking radiation. The universe gets colder, emptier, darker. And time? It just keeps stretching. Dilation becomes extreme, because with no nearby mass or motion to define now, everything becomes infinitely spread out. In a Big Freeze scenario, time never technically ends, but nothing meaningful happens anymore. The clock keeps ticking, but the party's over. Entropy wins. It's like the last 5 people at a wedding reception, dancing quietly in an empty hall while the DJ packs up. But that's not the only theory. Some physicists believe dark energy may not stay constant. What if it gets stronger? What if its repulsive power increases over time? That leads us to a more dramatic finale, the Big Rip. Yes, it's exactly what it sounds like. In the Big Rip, the accelerating expansion of the universe becomes so extreme that it doesn't just push galaxies apart, it tears galaxies themselves apart, then solar systems, then planets, then atoms. Time doesn't just stretch in this scenario, it fractures. Eventually everything, matter, space, and yes, even time, comes to an end. Not in a bang, but in a catastrophic unzipping of the very fabric of space-time. The timeline just snaps. How soon would this happen? Well, not soon by your standards, maybe in 20 to 30 billion years, if it happens at all. But in cosmic terms, that's tomorrow. And of course, there's the classic favourite, the Big Crunch. This is where the expansion of the universe slows down and reverses. Gravity takes over. Galaxies fall back together. The cosmos shrinks. Time, instead of expanding, collapses inward. Some believe this could result in a new Big Bang, a cyclic universe, forever bouncing between expansion and contraction, birth and rebirth. But there's no evidence, yet, that the universe is heading this way. Observations point more toward acceleration, not reversal. Still, the idea of time folding in on itself, fascinating. And it leads us to the most speculative theory yet, the Big Bounce. A twist on the crunch idea, the Big Bounce suggests the universe didn't begin from nothing, but from a previous universe that collapsed and rebounded. That maybe time has already ended and restarted countless times. That your now is one cycle among many. Historians still argue whether ancient cosmologies, those cyclical time myths from Hinduism or Greek philosophy, somehow intuited this pattern. It's probably coincidence. But then again, time has a funny way of repeating itself. Now let's get weirder. There's a hypothesis floating around in the deep end of physics called vacuum decay. The idea is that our universe may not be in its most stable possible state. Instead, we might be living in a false vacuum, a temporary condition that looks stable, but could, at any moment, pop like a soap bubble. One tiny quantum fluctuation, one spontaneous blip, and a bubble of true vacuum could form, spreading outward at the speed of light, rewriting the laws of physics as it goes. New constants, new forces, new time. Your atoms, gone before they knew what hit them. Not because something came and destroyed you, but because reality itself changed into something else. Comforting, right? But don't worry, if vacuum decay happens, you won't feel it. It would be instantaneous and painless. like turning off a light. One moment, time. The next, nothing. And yet, even that possibility reminds us that time may not be eternal. It may not be permanent. It may be a condition, an emergent property of our particular universe. If the universe changes enough, if the field that defines time's flow disappears or transforms, then time as we know it could simply cease to be a thing. Which brings us to the ultimate question: what is time really? We experience it, we measure it, we age by it. But physics can't agree on whether it's fundamental or emergent. Some physicists now believe time might arise from entanglement and information processing at the quantum level, that the arrow of time is just a side effect of entropy increasing. That time isn't a thing, it's a description of change. So what happens when there's no more change? Does time die? Some future physicists may discover the final chapter in the story of time, but for now we're in the middle. The universe is still expanding, galaxies are still forming, your clock is still ticking. But maybe, just maybe, all of it is headed somewhere strange, or nowhere at all. And as you drift off, here's a soft thought to carry with you. If time ends, will it end for you? Or will you, like the stars and the black holes and the particles in the void, simply become part of a frozen moment? A final, still frame in the longest movie ever made? Either way, don't worry. You've still got time. By now you've travelled across centuries and light years, crawled near black holes, floated beside ancient stars, and even peeked into the future's possible unravelling. But let's take a turn tonight. Let's peek sideways, into the wonderfully weird and speculative question no physicist can fully answer. What if aliens exist and their clocks don't tick like ours? Because if there's life out there, and come on, odds are in favour, it might not just look different or think differently. It might experience time in a completely alien way. Their now might not line up with yours, their sense of before and after, possibly non-existent. Their memories may be stored backwards, or sideways, or in a medium that doesn't even rely on time as we understand it. So tonight, let's explore the mind-bending idea of alien clocks and extra dimensions. First, time, as we know it, is experienced linearly. Cause leads to effect. A hand moves across a clock face. Your coffee cools. You stub your toe, then swear. One thing after another. This is time on Earth. But is that the only way? What if an alien species evolved in an environment where time wasn't just one dimension, but part of a higher dimensional space? What if they didn't crawl through time like us, but could see it like a landscape? Past, present, and future all at once. Some physicists have speculated that higher dimensions, beyond our familiar 3D space and 1D time, might hold the key to unifying the laws of physics. String theory, for instance, posits up to 11 dimensions, most of them curled up so tightly we don't perceive them. But what if some beings do? A species native to a region where extra time-like dimensions exist might perceive multiple temporal directions, just like we perceive left and right, up and down. They wouldn't live in time, they'd live around it. Imagine trying to have a conversation with them. You ask a question, they answer before you speak. You introduce yourself. They already know your entire lifespan. To them, your life is a sculpture, a whole object, all at once. This isn't just science fiction fluff. This is a legitimate area of speculative physics. Some models even propose that time may behave differently in different parts of the universe, depending on the shape of space-time or the energy fields that fill it. That means their local version of time might run faster, or slower, or loop, or branch. And if aliens evolved in such conditions, then their biology, cognition, and language would be shaped by that time. A simple example, here on Earth, most organisms age in a forward linear progression. Our biology assumes that. Cells divide, memories form, muscles tire. But what if alien evolution occurred in a low-gravity environment near a massive object, where gravitational time dilation is extreme? That life would have adapted to a different tempo. Their chemistry might unfold slowly compared to ours. Their neural signals might be glacial, their day might last centuries, and their entire evolutionary cycle could play out over millions of Earth years. To them, humans might seem like frantic little mayflies, buzzing through a whole culture in the blink of their eyes. Or reverse the situation. Imagine a species whose biology evolved in a region of minimal gravity and low entropy, where the passage of time is barely resisted by physical processes. Their thoughts could be lightning fast. Their entire civilization might rise and fall in what we perceive as a second. We'd never even know they were here. Here's a fringe but intriguing idea. If a civilization developed near a black hole, not on the surface obviously, but orbiting just outside the event horizon, time dilation would make their clocks run much slower compared to ours. They could, in theory, observe our entire history, watching millennia unfold in what feels like a year to them. They'd be cosmic historians, quietly watching the fast-forwarded lives of distant beings like us. Which leads to a curious possibility. Maybe we haven't seen aliens because we're moving too fast for them to interact meaningfully, or too slow. Maybe the timelines just don't line up. Historians still argue whether this timescale mismatch could be a factor in the famous Fermi paradox. The question of why, in such a vast universe, we haven't yet encountered intelligent life. Some theories suggest they're avoiding us. Others say we're alone. But maybe we're just moving through time on different tracks, close enough to miss each other completely. Let's flip the concept again. If aliens exist, and their clocks are based on quantum fluctuations, stellar pulses, or even entangled particles, then their notion of time might not be sequential at all. They might communicate in bursts of pattern recognition, or memory clusters that are non-linear. Their technology might not use timers or schedules, but instead rely on entangled states that transcend time completely. They might look at our atomic clocks and think, cute, but terribly inefficient. They could be aware of time in ways we haven't even invented language for, and their timekeeping tools, possibly more like instruments than clocks, devices that listen to the hum of space-time itself, or devices that manipulate temporal flow the way we bend light. Could their technology allow them to move through time? Maybe not in the science fiction jump to the past sense, but in a more nuanced, physics-approved way, positioning themselves in frames where time behaves differently. Time travel by environment, not by machine. Even now, some scientists dream of time-tuning structures, shelters built in high-gravity zones, allowing a civilization to experience long stretches of existence while only a short time passes outside. Imagine a species that's been hiding, not in space, but in time. You can't find them because they aren't now, not in your now anyway. They might be behind us, or ahead, or perpendicular, whatever that means in space-time. And maybe they've already visited, dropped by when the planet was just microbes and lava, left before the pyramids, or maybe they'll arrive when we're long gone, excavating our concrete fossils and wondering why we were always in such a rush, because maybe the deepest difference between us and them won't be language or biology or chemistry. Maybe it'll be tempo. They'll look at us and ask, why did they live so fast? And we'll never hear the question because we'll be dust by then, blown away on a timeline that never intersected theirs. But for now you're here, in your own frame, your own tempo, your own private now. And even if the stars hold no aliens, no extra dimensions, no slow-walking civilizations near black holes, you can still look up and imagine them. Quiet observers, other clocks, other kinds of time. You've made it. Not to the end of time, that's still far, far off in some speculative corner of the universe, where heat death, black holes, or bouncing multiverses await. But you've made it to the end of our journey. And for this last leg, let's pull back. Way back. Let's zoom out until the galaxies are pinpricks, until time isn't something you measure in hours or years, but in structure, in the shape of the universe itself. Because what if time isn't a straight line? What if it's not even a loop? What if time is a shape? You've heard it before. Space and time are woven together into something called spacetime. Einstein taught us this. Mass bend spacetime. and that's what gravity is. But this idea doesn't just affect how things fall, it affects how time flows. And the deeper physicists have gone into this fabric, the more they've realised time might not be as simple as a river flowing forward. It might be more like a tapestry or even a geometry, a thing with curves, ridges, wrinkles and folds. Let's start small. You're sitting here on Earth, feeling the pull of gravity. That pull is not just space warping, it's time warping. Clocks on the surface of Earth run slightly slower than clocks on a satellite because Earth's mass bends the fabric of space-time downward, like a bowling ball on a trampoline. So time isn't constant, it's topographical. It has highs and lows, valleys and peaks. You are literally standing in a time well. Now scale that up. Picture the solar system, warped by the sun's mass. Then the galaxy, twisted and tugged by billions of stars in a supermassive black hole at the centre. Then the cosmic web, the enormous threads of matter that stretch between galaxies like a neural network made of stars. What does time look like there? Is it smooth? Jagged? Is it faster in the voids, where space is nearly empty? Slower near galaxy clusters, where matter clumps and twists the cosmic fabric? Physicists have begun to model time not as a constant flow, but as a field, something that changes depending on where you are and how fast you're going. Time has curvature, time has texture. Some theories even suggest that time could be non-orientable. That means you could, in principle, take a long enough journey through warped space-time and return to your starting point flipped in time, as if you'd walk through a Möbius strip of causality. It sounds wild, but mathematically, it checks out in certain solutions to Einstein's equations. These aren't just imaginary doodles on a blackboard, they're consistent models of reality, ones we haven't yet ruled out. Historians still argue whether time has a beginning or an end, or if those concepts even make sense in a curved, expanding, possibly infinite universe. Because here's where things get even stranger. In the realm of conformal geometry, time isn't infinite. It's finite, but unbounded, like the surface of a sphere. You can walk forever without reaching an edge, but there's still a total area to cover. In this model, the Big Bang wasn't a singular point in time, it was the entire boundary of a curved universe, and the end of time might not be a sudden stop, but a return to that same boundary, just from another direction. So time becomes circular, but not in a Groundhog Day way. It's not repeating events, but repeating conditions. The physics at the end might look like the physics at the beginning, a full cycle, a rhythm. And what about entropy? The one thing that seems to define time's direction. In some of these cyclic models, entropy resets. The arrow of time emerges again, pointing forward, but in a new universe, with new particles, new stars, new people, new you? Maybe not, but a new version of time, a new way of being, and maybe a new chance to wonder all over again. There's even a daring idea called conformal cyclic cosmology, proposed by Roger Penrose, which suggests that the universe goes through infinite cycles, or aeons, each separated by an event where time becomes so stretched out, so diluted, that the universe forgets its own age. Time flattens, boundaries blur. A new Big Bang emerges not from nothing but from infinite age. From the ashes of slow time, fast time is born again. That's not science fiction. That's serious mathematical cosmology, with equations and models and research papers that people argue about in university hallways, while sipping bad coffee and questioning the meaning of existence. And then there's the more philosophical idea, the one that might keep you up or lull you into a sense of strange peace. What if time isn't even real? What if it's a byproduct of consciousness? A story your brain tells you to make sense of entropy and memory and causality. In some interpretations of quantum mechanics, like the block universe model, time doesn't flow at all. It just is. All events, past and future, exist simultaneously. You just experience them in order because that's how your mind processes information. In that case, your birth, your thoughts, your dreams, your last breath. It all already exists, permanently embedded in the structure of space-time. And your experience of moving through time is just that, an experience. It feels real because you're in it. But from outside, you're a static sculpture, a four-dimensional masterpiece, all at once. So what now? Well, if you followed this story from the first sleepy whisper of the Big Bang to the strange curves of cosmic time, then maybe you're not looking at clocks the same way anymore. Maybe your heartbeat doesn't feel quite so tied to the ticking of a second hand, because time, true time, is wild, wobbly, warped. It's not the neat little number your phone shows you. It's not even linear. It's a shape, a force, a condition, a backdrop, a character in the story that also is the story. And you? You're a ripple, a moving point, a lived moment. You stretch and bend along with it, caught in time's current, but also shaping the flow in ways no clock can measure. So the next time you feel like time's rushing past or dragging or looping or skipping, remember, it's not broken. It's just complicated and quietly, beautifully alive. So now, here you are, at the edge of time's strange and winding path. Not at the end of the universe, not by a long shot, but at a quiet pause in the story, a soft place between seconds where clocks don't tick and galaxies don't rush. The stars above you, still expanding away, slipping deeper into redshift, their light stretched thin across the black velvet of space. But down here, everything is still, or close to it, and you, well, you've been floating along through dilation, distortion and debate. You've tiptoed across black hole edges, danced with muons, borrowed the viewpoint of ancient stars, and pondered the tempo of aliens whose now might never touch yours. You've listened to the universe whisper its slow truths, where nothing ages quite the same, and time is always relative, always bending. So breathe in, let your thoughts stretch, like light on a journey through space. Let them slow, like a clock falling into the curve of a massive planet. Let your body soften under the pull of gravity that's been warping your time all along, gently, invisibly, constantly. You're not behind, you're not ahead. You're exactly where you're meant to be in your own frame, flowing through time at your own rhythm. Because time is not a race, it's not a trap, it's a landscape. And right now, you're resting on the quietest hill, under the softest sky, while the cosmos spins on without urgency. Sleep well, time traveller. There's nowhere to be but here, and all the time in the world to simply drift.